Hi, everybody. Welcome to Chapter 8, Part 1. This is an important chapter. This chapter is the basis of all the hypothesis testing that we're going to do in this class. This is a crucial chapter. So this is more of a conceptual chapter instead of like a computational kind of a chapter. But, man, these concepts are important. It is really, well, it's important. All right, let's do some review. And so this is review stuff you should already have in the back of your mind. Here we go. I think that sleep makes you happier. I measure how many hours of sleep you had and then measure your happiness using a Likert scale. How many variables and what are they? Okay, this would be two continuous variables. Hours of sleep would be ratio, and happiness using a Likert scale, that's a agree to disagree kind of a thing. That is an ordinal measure. Both of those we chunk together as continuous data. So these are two continuous variables. Now the reason why this is important is because you need to be able to recognize which statistic to use in order to test your hypothesis. So that's coming up in future chapters later on. All right. Tell me whether or not you're left-handed. Okay. Now, tell me what kind of data that is. That is categorical data. You're either left-handed or you're right-handed. It's not like one is better than the other. It's just different, okay? Different categories, left-handed, right-handed, categorical. Remember, this is important to know what statistic you're going to use later on. This is all review. Let's move on to stuff from Chapter 8. Here it goes. So we need to understand a sampling distribution of a statistic. You remember a statistic is the actual the number that's associated with the sample. When we are using statistics, though, we often use it with hypotheses. So my hypothesis is that wearing glasses makes me more attractive, for example. Well, if I run a statistic based off of wearing glasses makes me more attractive, and like, what is my hotness scale? There's different statistics that we could run, right? If I run the statistic, whatever value the statistic gives me, let's say I get a 23.86. Well, a sampling distribution is all the possible values of a statistic if wearing glasses has nothing to do with my hotness. Could I have gotten a 28.56 or whatever that score was? Could I have gotten that even if my hypothesis was not correct, even if glasses had nothing to do with my actual hotness? That is the point of everything that we're going to be doing. Whenever we get a statistic, it tells us, it tells us, hey, this is what's going on. It's like a numerical representation of a relationship between variables, right? We have to figure out, could we have gotten that when there actually is no relationship between the variables? So, for example, remember we've been talking about Ricky Martin in Menudo. If you remember, Ricky Martin has a higher average tenure in Menudo. He was in Menudo longer than the average. So our hypothesis might be that Ricky Martin was so talented that it caused him to be in Menudo longer, right? Okay, so hypothesis talent made him stay longer in Menudo. The sampling distribution is all the possible values, right, that a statistic could take. So all the possible values of tenure that the statistic could take. And what is the probability of getting that randomly, by chance, if his talent had nothing to do with him staying in Menudo? And then we say, all right, well, he got this. And, the probability of getting that when there's nothing going on is either really high or really low. And then we make a decision as to whether or not we really think it was his talent that was causing his tenure in Menudo. So let's move forward with this. This is the first two steps of how to analyze statistics. And boy, these basic two steps, these are everything, right? So number one, you calculate the appropriate statistic. You got to know what statistic you're going to run. That depends on how many variables there are. That depends on whether they're categorical or continuous. That depends. So we're not going to dwell on that right now, but boy, that's an important thing. If you run the wrong statistic, then everything else is garbage. So step one, calculate the right statistic. And that depends how many variables, how many levels of the variable, what kind of data you're getting, all that. Step two, though, is to evaluate the statistic based off its sampling distribution. Now remember, all you're doing with that is saying, all right, here's what I got. I got a 28.75. What's the probability of getting that if Ricky Martin's talent had nothing to do with his tenure in Menudo, right? Or what's the probability of me getting a 25.86 if wearing glasses has nothing to do with your attractiveness? And then we're going to make that decision, all right? That's part of the evaluation. So here's another analogy. Statistics are like pregnancy tests. When somebody takes a pregnancy test, they don't know whether or not they are pregnant. They don't know what's really happening. They take the test. The test tells them they're either pregnant or they're not pregnant. So that test, whether you're pregnant or not pregnant, that's kind of like a statistic. Now, statistics always tell you you're pregnant, right? They're always saying, all right, here's the numerical representation that's a relationship between the variables. So statistics basically always tell you you're pregnant. Think of a statistic like a pregnancy test that always tells you you're pregnant. And then you got to say, well, what is the probability that I would get this positive pregnancy test when I'm not pregnant? That's what we're doing. That's what we're doing here. We're saying every statistic that we calculate, almost every, but the vast majority of statistics are saying, hey, there's a relationship between these variables. They're saying, hey, you're pregnant. And then you say, well, what's the probability of you telling me that I'm pregnant when I'm not pregnant? That's an important question. And it gets us to the idea of errors and hypotheses and null and all that stuff, which is so good. Okay. In science, we do not prove things. We have evidence that the opposite is false, but we never say that we prove stuff, right? So let's say I did my glasses and hotness test, right? My glasses and hotness test, my hypothesis is that wearing glasses makes you hotter, right? Now, in the world, we can never go out and measure every person in the entire world, have them wear glasses, measure their hotness, have them not wear glasses, measure their hot. We just can't do that. So we never know for sure if wearing glasses actually in the whole population makes you hotter. We can only guess. So that means that we actually, when we do statistics, we're looking at the null hypothesis, which we'll get to in just a second. So my hypothesis that glasses makes you hotter is actually called the alternative hypothesis. Normally we don't use that word alternative because, we don't think about it, but it's alternative to the null. It's alternative to nothing. Okay, does that make sense? So when I say, hey, glasses makes you hotter, that's the alternative hypothesis. There's a relationship between the variables. In this case, one variable is glasses and the other variable is hotness. There's a relationship. That alternative hypothesis can be directional or non-directional. Directional means wearing glasses makes you hotter. The direction is it can only go to hot, right? It can only make you hotter. It's not going to go the other way, not hotter. Non-directional says wearing glasses affects your hotness. It could make you be hotter. It could make you be notter, right? It could make you be more attractive or it could make you be less attractive. It's non-directional. It could go either way. The null hypothesis is that there's no relationship between the variables. Okay? So for example, the null hypothesis for my glasses hypothesis, remember the alternative hypothesis is that glasses makes you hotter. The null hypothesis is that glasses has nothing to do. Null means nothing. Nothing to do with hotness. Right? Glasses, nothing. None. Nothing. The null is no relationship. Nothing to do with it. Now, technically, if you're saying that it can only make you hotter, the null could include that it could make you less attractive. But in general, the way I want you to think about null hypothesis is null. No relationship between the variables. The alternative hypothesis is glasses affects my hotness. The null hypothesis is glasses has nothing to do with my hypothesis, with hotness. Glasses doesn't do anything with hotness. All right. So let's test you out with this. When we do the null hypothesis, we are looking at the probability, whenever we do any test, we're looking at the probability of whether we should reject or fail to reject the null. So our outcome is always based off of the null hypothesis. We never go out and say, oh, I have proved that wearing glasses makes you hotter. We don't do that. Instead, I go out and do my statistic. My statistic is a 57.993. The probability of doing that is super, super small if the null is true. Remember, the null hypothesis glasses has nothing to do with hotness. So getting a 57.993, probability of getting that when glasses has no effect on my on hotness, the probability of doing that is super, super small. My conclusion is that I can reject the null. Rejecting the null means that I think that glasses does affect your hotness. Or I can fail to reject the null. Failing to reject the null means that I don't have enough evidence to say that wearing glasses actually affects your hotness. When you come to a conclusion in any study that you do, you are either going to reject or fail to reject the null. So let's do a little test here. What's the null hypothesis for Ricky Martin? Remember, the alternative hypothesis was that that Ricky Martin's talent led to a longer tenure in Menudo. So what is the null hypothesis? The null hypothesis is that Ricky Martin's talent had nothing to do with his tenure in Menudo. Okay? What does it mean to reject the null hypothesis for Ricky Martin? If we reject the null hypothesis, then we're saying that his talent did have something to do with his tenure in Menudo. If we fail to reject the null hypothesis, we're saying that Ricky Martin's talent had nothing to do with how long he was in Menudo, nothing to do with his tenure in Menudo. Okay? When we come to a conclusion in any test that we do, we are either going to reject or fail to reject the null hypothesis. And this leads us to type 1 and type 2 errors. Type 1 and type 2 errors. So let's go ahead and draw this out. So here's what we're going to do. All right. It told me I was out of batteries, and then it did evil things to me. So come back to me. Type 1 and type 2 error. So type 1 and type 2 error, we are going to draw this box right here. Up here, this is real life. Let's use my example with glasses. All right. Glasses, my hypothesis, remember my alternative hypothesis, my alternative was glasses affect your hotness. Okay? So that's my alternative hypothesis. That means that the null hypothesis, remember we call the null hypothesis H sub 0. The alternative hypothesis, by the way, is called H sub 1, depending on how many hypotheses you have. So H sub 0 is going to be glasses doesn't affect on hotness. Okay? That's going to be my null hypothesis. Notice no effect, null, null. In real life, the null is true or the null is false. But we do not know. We don't know. We don't ever know because we can't go out and we can't test every single person in the world to figure out whether or not they're wearing glasses or not. Okay? So in real life, either glasses affects your hotness or it doesn't affect your hotness. But we actually don't even know if the null is true or if the null is false. Instead, we come to our own conclusion based off of our own study. Our conclusion, which is going to be the rows here. So our conclusion is either going to be to reject the null. That says reject H sub 0. Or fail to reject the null. Remember, failing to reject the null is coming to the conclusion that hotness doesn't have any effect. The glasses doesn't have any effect on hotness. In real life, it's either true or it's false. But then you're going to come to your conclusion. You're going to say it's either true, we're going to reject the null, we're going to fail to reject the null. So if you reject the null, that means, hey, I conclude that glasses affects your hotness. And the null is false, that means glasses affects your hotness. Then you're correct. This is up here. Okay? But if you fail to reject the null, you say, based off of our analysis, we can't say that glasses affects hotness. And in reality, glasses doesn't affect hotness, then you're right here. The null is true, and you fail to reject the null. That's good. Now, I know this is like double and triple negative, but remember, we don't prove things correct. All we do is give evidence that, that the null is either true or it's false. So the errors are here. Type 1 error. Now, those are Roman numerals up there that I have in the printed one. But I don't care if you use Roman numerals or if you don't. It doesn't really matter to me. Type 2. Okay, so the type 1 error is when you reject the null hypothesis when the null hypothesis is true. Okay, what's the null hypothesis? The null is that glasses doesn't affect your hotness. Null, no effect. If you reject the null, then you're saying glasses affects hotness. So if my conclusion is glasses affects hotness, when in reality it does not, I've made an error. I've just published to the world that glasses affects hotness. Hey, everybody, glasses is going to make you hotter. But in reality, it doesn't. That's a problem. That's a big problem. The type 2 error is when you fail to reject the null when the null is false. So you do your study and you say, boy, based off our results, we cannot say that glasses affects hotness. We fail to reject the null. But in reality, glasses does affect hotness. The null is false. That's a type 2 error. In that case, you concluded that it doesn't affect anything, but in reality it does. That's a type 2 error. Type 1 error is when you go out and publish to the world that this is going on when in reality it's not. Type 2 is when you say nothing's going on when something really is going on. Okay? So, give me an example of a type 1 error if the pregnancy test, on the pregnancy test. So what is a type 1 error for the pregnancy test? The type 1 error is you calling up your mom and saying, hey mom, I'm pregnant, when in reality, you're not. The null hypothesis is nothing's going on, you're not pregnant. To reject the null means you're concluding that you are pregnant. So you conclude you are pregnant when you're not. That's a type 1 error. All right, generally in science, the type 1 error is the one that we're most scared of. But that doesn't always have to be the case. It doesn't have to always be the case. It could be the opposite. So let's say that you are looking for landmines, right? So you're working with a crew, you're looking for landmines. Landmines are things that they put in the ground, you step on them and it explodes and kills people. It's a huge problem. There's still parts of the world that are clearing out landmines. So let's say you've got this metal detector and the metal detector goes off. It says, hey, something's there. Now, you don't know for sure. You don't know for sure whether something's there. This beep, 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 beep is telling you something is there. Now, underneath the ground, it could have been a false alarm or it could be real. So let's say that your metal detector beeps, and that means that you would reject or fail to reject the null. That means that you would reject the null, right? Your beeper beeps, and then it's saying, hey, something's there. Okay, the null is nothing's there, right? So we're rejecting that null. A type 1 error is it beeps, beep, 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 but in reality, there's no landmine there. Okay, now that's not a big deal. A type 2 error is a big problem for landmines. In that one, your test doesn't say anything's there, but in reality, something's there. So it's like you walking around and your metal detector doesn't go off, and then you step on a landmine. That's a problem. So in reality, we do not know what's actually happening. We do not know what's actually happening. So that means that we got to make certain standards of what we're going to do. Because remember, the statistic is like a pregnancy test that always tells you you're pregnant. Always, always, always. The statistic is always telling you that there's a relationship between the variables. And you got to figure out whether or not you're going to believe it. So that means you got to figure out what your standards are. Alpha. So that A at the top, that's actually the Greek alpha. Alpha is the probability that you are willing to accept of making a type 1 error. So it's saying, all right, well, what's the chance of me saying I'm pregnant when I'm not that I'm willing to take? It's you thinking of, gosh, what is the probability I'm willing to accept of calling up my mother saying I'm pregnant when in reality I'm not pregnant? That is the standard you're setting. That is alpha. Alpha is up to you. You get to decide how strict you're going to be. If it's something like a pregnancy test, people tend to be pretty strict. Maybe you'll only accept like a 0.1% chance of you saying that you're pregnant when you're really not. Okay? But for other things, it might be a little bit different. So for like the landmine thing, maybe you're willing to accept, 50% chance of saying that there's a landmine when there's not, right? This depends on you. Now there is an established standard, and that is 0.05, a 5% chance. That's generally what we use in most science, but specifically in psychology, is a 5% chance. However, in reality, you get to choose what you're willing to do. Now, the next thing is the p-value. Remember, alpha is the standard you're willing to accept. You get to decide what the standard is. The p-value is the probability of getting the statistic when there's no relationship in the population. So the p-value, let's say that I ran my statistic about glasses and hotness, and I got the statistic of 58.75. There would be a p-value, a probability of getting 58.75 if glasses had nothing to do with hotness. It's a separate probability. It's the probability of getting a 58.75 when there's nothing to do, when glasses doesn't have anything to do with your hotness. If your p-value is less than your alpha, that is good. That means that you have a small chance of making a type 1 error. There's a small chance of you calling your mom saying you're pregnant when you're not. Instead, you're more likely to actually be correct. Beta is the probability you're willing to accept. It's the chance of making a type 2 error. Now, this does depend on your alpha, and we'll talk about it at a later date. So alpha is the standard you're willing to accept of making a type 1 error. Beta is the probability of making a type 2 error. Effect size is totally different from this, though. The effect size is how big of an effect does wearing glasses have on my hotness. So wearing glasses could only have a small effect, but there's still an effect, or it could have a huge effect and make me really hot. That would be a big effect size. That's different than the probability of me getting any statistic when the null hypothesis is true. That's a different thing. It's not the same. All right. Let's ask you this, and then we will be done. Which of these do you get to make up? Which of these do you get to just make up out of your brain? The answer is alpha. You get to make up your alpha. That's the standard you're willing to accept of making a type 1 error, and you get to make that up. All right, thanks, everybody.